Hello students, in today's lecture we are going to learn about mechanical properties of fluids. NCERT section 9.4.1 to 9.4.2. Example 9.7. This is disclaimer. Learning objectives. By the end of this lecture you will be able to understand Torricelli's law for fluid efflux from containers and calculate exit velocity using Bernoulli's principle. Explain the mechanism of dynamic lift in airfoils and analyze factors affecting lift force generation using Bernoulli's equation. Now in this lecture we are going to cover 9.4.1 speed of efflux, Torricelli's law, then 9.4.2 dynamic lift, and last we will solve an example 9.7. Now let's understand how fast a fluid exits and opening using something called Torricelli's law. So first let's define the term efflux. This is very important. Efflux simply means the outward flow of a fluid. Alright. For example, think about water coming out of a tap or a air rushing out of a balloon. These are both everyday examples of efflux, and understanding this will help us make sense of the physics behind fluid movement. Alright. Efflux means outward flow of a fluid. So the word breaks it down into EF meaning out and flux meaning flow. So efflux literally means outflow. This breakdown helps us remember that we are always talking about something flowing out, not in. Alright. Now let's look at what Torricelli discovered. He found that the speed at which a fluid exits an open tank is the same as the speed a body would have if it fell freely from the same height as the fluid level above the opening. Torricelli's law shows us a surprising link between fluid flow and projectile motion. Just like a ball dropped from a height gains speed as it falls, fluid exiting a tank gains speed based on how high the fluid is above the opening. So let's see what Torricelli's law says. We will look physical setup and mathematical formulation of Torricelli's law. Torricelli's law states that the speed of efflux fluid flowing out from a hole in a container is equal to the speed acquired by a freely falling body through the height of liquid above the hole. So this result is remarkable because it shows that all the gravitational potential energy of the fluid at a height h is converted into kinetic energy as it exits the hole, just like an object in free fall. Alright. So uh, let's look at a physical setup. So consider a tank containing liquid of density rho with a small hole at height y1 from the bottom. Look at figure 9.10. Alright. So height is y1, this one, from the bottom. this one. Y1 is the height. Similarly, uh, here y2 is another height. Liquid surface is at height y2 and air above the liquid is at pressure P. Alright, this one. So, let's see the mathematical analysis. From continuity equation, A1 V1 equal to A2 V2. Alright, here A1 and A2 are the cross sectional areas at two different points in the flow, and V1 V2 are the fluid velocities at those points. All areas are measured in square meters and velocities in meters per second. So we can rearrange the equation to solve for V2. So V2 equal to A1 divided by A2 into V1. This means that the velocity at point 2 depends on the ratio of the areas and velocity at point 1. So if the tank's cross-sectional area A2 is much greater than the area of the hole A1, we can assume the fluid at the top of the tank is almost at rest. In other words, a V2 is approximately 0. This simplifies our calculations and is a common assumption in these problems. Alright. So now applying Bernoulli's equation between 2 points. Point first at the hole and point second at the surface of the fluid. So the Bernoulli's equation for this situation is PA plus 1 by 2 rho V1 square plus rho G Y1 is equal to P plus rho G Y2. Here PA is the atmospheric pressure at the hole, rho is the fluid density, V1 is the velocity at the hole, G is the acceleration due to gravity, and Y1 and Y2 are the heights at point first and second. Remember, PA stands for atmospheric pressure, which is the pressure exerted by the air at the hole. Now, let's start by solving exit velocity. So, we have PA plus 1 by 2 rho V1 square plus rho G Y1 equal to P plus rho G Y2. Alright, this equation balances energy at 2 points in the fluids. Rearranging the above expression, alright, to isolate the kinetic energy term which involves velocity. So 1 by 2 rho V1 square is equal to P minus P1 plus rho G Y2 minus Y1. This shows that both the pressure difference and the height difference contribute to the fluid's exit speed. So we solve for V1. So V1 square equal to 2 into P minus PA divided by rho plus 2G Y2 minus Y1. Alright, this is the formula for exit velocity using Torricelli's law, and this is very important formula. Now, taking Y2 minus Y1 is equal to H. Here, Y2 minus Y1 is the difference, vertical height difference. So, where H is the vertical distance between the fluid surface and the exit point. So, general formula for the velocity of the fluid at the exit point. The equation V1 square is equal to 2 into P minus PA divided by rho plus 2GH. Here V1 is the exit velocity, P is the pressure at the fluid surface, PA is the atmospheric pressure, rho is the fluid density, G is the acceleration due to gravity, and H is the height. So if we solve for V1, we get V1 equal to under root 2GH plus 2 into P minus PA divided by rho. This is the important equation. Now let's consider a special case. What happens if the container is open to the atmosphere? So for an open container, the pressure at the fluid surface P is equal to the atmospheric pressure, which is PA. That means the pressure difference term becomes 0. Alright, and only the height matters. So in this special case, the exit velocity formula becomes V1 equal to under root 2GH, which uh, which is important relation. This tells us that the speed of the fluid depends only on the height of the fluid above the exit point and gravity. So from this equation 9.15, it is clear that speed of the fluid depends only on the height of the fluid and uh, gravity G and H. Alright. Now connection to free fall. So let's make a connection between Torricelli's law and the concept of free fall. So Torricelli's law is directly analogous to the velocity a body gains when it falls freely under gravity. In other words, the speed of the fluid exiting the hole is similar to the speed an object would reach if it fell from the same height. So now imagine dropping an object from the rest from a height h. The final speed is reaches just before hitting the ground is the given by the specific formula. This is the same formula that describes the exit speed of the fluid. So V equal to under root 2GH, assuming air resistance is negligible. Alright, in this equation, V is the final speed in meters per second. G is the acceleration due to gravity, which is about 9.8 meter per second square, and H is the height in meters. This means that if you increase the height, the exit speed increases as well. Now we will understand what dynamic lift is and the physical principles behind it. Dynamic lift is a key concept in the mechanical properties of fluids, specifically when objects move through air or water. So now let's examine what dynamic lift actually means. When a body moves through a fluid like air or water at an angle, it creates a pressure difference between the top and bottom surfaces. This pressure difference results in a force that can push the object upward or sideways. For example, this is the same principle that allows airplanes to stay in the air. So, during the game of cricket, tennis, baseball, or golf, a spinning ball deviates from its parabolic trajectory during its motion in the air. It does not follow a simple parabolic path. The spin creates a pressure difference, causing the ball to curve or dip unexpectedly. This is why players can use spin to control the ball's movement. So now let's understand examples of dynamic lift, which is a key concept in a mechanical properties of fluids. Dynamic lift refers to the upward force that acts on objects moving through a fluid, like air or water. Alright. So first, let's focus on a ball moving without spin. This means the ball is just moving straight through the air, not rotating at all. Now, look at the streamlines in the figure 9.11. Fluid streaming past a static sphere. Alright. For a non-spinning ball moving through a fluid, the air flows symmetrically around it. Alright. Symmetrically around it. The streamlines above and below the ball are my mirror images. This symmetry means that the velocity of the air at points directly above and below the ball is same. Because of the velocities are equal, there is a no pressure difference between the top and bottom of the ball. So since there is a no pressure difference above and below the ball, the air does not create any net upward or downward force on it. In other words, the ball does not experience any lift due to its motion through the air when it is not spinning. So, when a ball moves through a fluid without spinning, the forces from the fluid are balanced above and below. So, there is a no lift. Alright. Now, second, ball moving with spin. Alright. So, the ball actually drags some of the surrounding air along with its surface as it spins. This interaction between the ball and the air is key to understanding how lift is generated in sports like cricket. If the surface is rough, more air will be dragged. So, look at figure 9.11b. This diagram shows the streamlines of air around a ball that is both moving forward and spinning. The streamlines bend differently on each side of the ball, which creates a pressure difference and leads to dynamic lift. Alright, this is the same principle behind the curve in a spinning uh, ball or a swimming cricket ball. For comparison, figure 9.11a shows what happens when a ball moves through the air without spinning. The streamlines are more symmetrical and there is a no extra lift generated by spin. This highlights how important spin is in changing the path of a ball in sports and understanding fluid dynamics. Now, look at the figure that the ball is moving forward. Alright, ball is moving forward. So, and from the ball's perspective, the air is moving backward. This is a key idea in physics called relative motion. Alright, it's all about how things move with respect to each other. Alright, so the figure shows different ways air flows around a ball. So, therefore, the velocity of air above the ball relative to the ball is larger and below it is smaller. This difference in speed is crucial because it sets up the condition for dynamic lift. Because of these differences in air speeds, the streamlines, those lines that show the path of the air, get crowded above the ball and spread out below it. Crowded streamlines mean higher velocity and lower pressure, while spread out streamlines means lower velocity and higher pressure. So, this difference in the velocity of air results in the pressure difference between the lower and upper faces, and there is a net upward force on the ball. Alright, this upward force due to the spinning motion is called Magnus effect. The Magnus effect explains why spinning balls curve in a sports like cricket, football, and tennis. It's a great example of how physics principles apply to real life situations. Now, let's talk about what an aerofoil is. So, an aerofoil is a solid object specifically shaped to create an upward force or lift when it moves horizontally through the air. This shape is designed so that air moves faster over the top surface when the bottom, which is a key generating lift. So, look at figure 9.11. It shows three different situations. A. Fluid flowing past a stationary sphere. B. Fluid around a spinning sphere. And C. Air flowing past an aerofoil. So streamlines which show the path of the fluid change in each case. Focus specifically on part C, where the air moves over and under aerofoil, creating the conditions for lift. So in figure 9.11a, we see streamlines found a non-spinning ball moving through a fluid. The lines are fairly symmetrical, which means there is a no net lift force acting on the ball. This helps us understand that just moving through a fluid is not enough to create lift. The shape and motion matter. Now let's connect this to airplane wings. The cross section of an airplane wings is shaped like a aerofoil in figure 9.11c, and the streamlines show how air flows faster over the curved top than the flatter bottom. This difference in airflow creates a pressure difference, resulting in an upward lift force. This is the principle that allows airplanes to fly. Now, look at the figure. Uh, Wing is tilted relative to the direction of the airflow. This tilt or angle of attack causes the air streamlines to bunch up or more above the wing than below it. The crowding of streamlines means the air is moving differently above and below the wing, which is to key to understanding lift. Emphasize how the shape and orientation of the wing affect the airflow. So, the speed flow, uh, the air moves faster over the top surface of the wing than it does underneath. According to Bernoulli's principle, when the speed of a fluid increases, its pressure decreases. So the higher speed on the top means lower pressure above the wing, while the slower air below means higher pressure underneath. So the difference in pressure creates an upward force called dynamic lift, which acts on the wings and helps balance the weight of the plane. Without this lift, the planes could not stay in uh, the air. So the combination of wing shape, orientation, and airflow speed is what allows aircraft to fly. All right. Example 9.7. A fully loaded Boeing aircraft has a mass of 3.3 into 10 raised to the power 5 kg. Its total wing area is 500 meters square. Uh, it is in level flight with a speed of 960 km per hour. A. Estimate the pressure difference between the lower and upper surfaces of the wings. B. Estimate the fractional increase in the speed of the air on the upper surface of the wing relative to the lower surface. The density of air is rho equal to 1.2 kilogram per meter cube. Alright, let's see the solution. So let's start by listing all the information given in the problem. Mass of aircraft m equal to 3.3 into 10 raised to the power 5 kg. Total wing area A equal to 500 meter square. Speed V equal to 960 km per hour. Now here speed is given in kilometer per hour. So we need to convert it meter per second. So just multiply by 5 by 18. So it will be 267 meter per second after conversion. Density of air rho equal to 1.2 kilogram per meter cube. Gravitational acceleration g equal to 9.8 meter per second square. Alright. Now let's start with part A, which is about estimating the pressure difference. This pressure difference is what actually keeps the plane in the air by providing lift. Remember, the weight of the aircraft is balanced by the upward force from the pressure difference across the wings. This is a direct application of Newton's third law. The plane pushes air down and the air pushes the plane up. The lift force, which keeps the plane aloft, is calculated by the multiplying the pressure difference delta P by changing wing area A. So the lift force is equal to delta P times A. Delta P times A equal to lift force. Alright. So substitute the values. So the mass of the aircraft is 3.3 times into 10 raised to the power 5 kg into 9.8. So it will be solving this. You will be get delta P into 500 meter square is equal to 3.3 into 10 raised to the power 5 kg into 9.8. Alright. Now solving for pressure difference. Remember, the pressure difference between the upper and lower surfaces of the wing is what generates lift to keep the plane in the air. So delta P is equal to 3.3 into 10 raised to the power 5 kg into 9.8 meter per second square divided by 500 meter square. Alright. So after calculating, we find that the pressure difference delta P is equal to 6.5 into 10 raised to the power 3 Newton per meter square. This means the air pressure under the wing is about 6500 pascals higher than above the wing. Alright, which is enough to support the weight of the aircraft. Now, uh, now let's focus on part B of the question. Here, we are told to ignore the small height difference between the top and bottom surfaces of the wing. This means we can simplify our calculations by assuming the heights terms in the Bernoulli's equation uh, are nearly equal and can be left out. So the Bernoulli's equation P1 plus 1 by 2 rho V1 square plus rho GH1 is equal to P2 plus 1 by 2 rho V2 square plus rho GH2. So since we are ignoring the height difference, the terms with G and H cancel out. So the equation simplifies to P1 plus 1 by 2 rho V1 square equal to P2 plus 1 by 2 rho V2 square. P1 minus P2 equal to 1 by 2 rho V2 square minus 1 by 2 rho V1 square. This shows us that the pressure difference between the lower and upper surfaces of the wing depends on the difference in the squares of the air speeds above and below the wing. Alright. Now let's focus on the pressure difference. The pressure difference between the upper and lower surfaces of the wing is what generates lift, allowing the plane to stay in the air. So P1 minus P2 is equal to 1 by 2 rho V2 square minus 1 by 2 rho V1 square. Alright. So delta P, P1 minus P2 is change in pressure. So delta P is equal to rho by 2 V2 square minus V1 square. This makes it clear that the pressure difference depends on how much faster the air moves over the top of the wing the compared to underneath. So where V2 is the speed of air over the upper surface and V1 is the speed under the bottom surface. So V2 minus V1 is equal to 2 times delta P divided by rho into V2 plus V1. Alright. Now taking the average speed. So V average is equal to V2 plus V1 divided by 2. In this equation, V2 is the speed of air over the upper surface of the wing, and V1 is the speed under the wing. So V average is equal to 960 km per hour. So here we need to convert kilometer per hour to meter per second. So it will be 267 meter per second. Remember, to convert from kilometers per hour to meter per second, it's very important. So we have V2 minus V1 divided by V average is equal to delta P divided by rho V square average equal to approximately 0.08. The speed above the wing needs to be or 8% higher than that below. Alright. So the small difference in speed creates the pressure difference that keeps the plane in the air. I hope this is clear. Now let's summarize what we have studied uh, so far in this lecture. So efflux refers to the outward flow of fluid, and Torricelli's law relates fluid exit velocity to the height of fluid above the hole. For an open container, exit velocity V equal to under root 2gh, which is identical to free fall velocity formula. The fluid exit speed from a tank depends on the height of fluid column and pressure difference, that is P minus PA. When A2 is greater than A1, tank area much larger than hole area. The surface velocity can be considered approximately 0. Dynamic lift occurs when a body moves through fluid at an angle, creating pressure differences. For a non-spinning ball, symmetrical streamlines result in no net lift force. Magnet's effect explains how spinning balls generate lift due to uneven air velocities above and below. Aerofoils aircraft wings are specifically shaped to create lift by causing faster airflow above and then below. Bernoulli's principle underlies all these phenomena. Higher velocity means lower pressure. The lift force depends on the shape, speed, and orientation of the object moving through the fluid. Now we have some practice questions. First, what is the formula for fluid exit velocity from an open container according to Torricelli's law? Why does the liquid surface level remain nearly stationary in a large tank when fluid flows out from small hole? What is the Magnus effect and how does it affect a spinning ball? How the streamlines different above and below an aircraft wing during flight? Why is there no net lift force on a non-spinning ball moving through air? All right. Thank you for your attention. I hope this lesson was helpful. Thank you.